In this section, we're going to do a lot of different things, including finding square roots of numbers, approximating square roots between two integers, ordering real numbers, evaluating cube roots, and classifying real numbers. So a square root, something to know about a square root is a lot of people think they know what a square root is, because they do. For example, the square root of 9 we know is 3, and we can prove that it's 9 by multiplying 3 times 3. What a square root really is it's one of two equal factors of a number. So it's really the number times itself. And so example, the square root of 36 is 6, because 6 would be the number that if you were to multiply it by itself would give you 36. Perfect square is any number whose square root is an integer. So think like a number like, for example, we just did 9 and 36. Their answers are basically just like positive numbers. They're not decimals, they're not fractions. And so the first perfect square is 1, because the square root of 1 is 1, but then it's 4, because the square root of 4 is 2, and then it's 9, 16. So pause the video. I want you to see how many more of these you can fill in on your own, and then we'll talk about what that means when you get there. Press play when you're ready to check your answers. So here are some more perfect squares so far: 25, 36, 49, 64, 100. For example, the square root of 100 is 10, the square root of 121 is 11, the square root of 144 is 12, 13, 14, and all this means is so on, and we could list unlimited numbers of perfect squares, but for now we're just going to stop there. So I just wanted to kind of expose you to some of these numbers that exist whose square roots are integers. So the next several examples are just designed to have you start evaluating with square roots, to just kind of get back into the swing of things. So for example, we know that the square root of 16 is 4. Square root of 64 is 8. So again, pause the video, try examples 5 through 8, press play when you're ready to check your answers. And so we've got 9, 10, 11, and 7. So now what we're going to do, we're going to think about the number 4. And what number times itself will have an answer of 4? And of course, you're probably thinking 2. And we could prove that by saying 2 times 2 equals 4. But is there any other number that you can think of that would also have an answer of 4 when multiplied by itself? So try to think for a second. If you took something and multiplied it by its exact self, could you also get those numbers to have an answer of 4? So I want you to think about that just for a few seconds. And were you able to come up with anything? Is there any number that you could think of? What about negative 2 times negative 2? And so a negative 2 times a negative 2, we know a negative times a negative is a positive, and then 2 times 2 is 4. So what that means for us is that 4 actually has 2 square roots. There are 2 different possibilities that if we multiply a number by itself would get us 4. 2 multiplied by its exact self gets us 4, but negative 2 multiplied by its exact self also gets us 4. So because of that, what we've noticed is that all numbers actually have 2 square roots. One is positive and one is negative. And your job is to just know which one are they asking you for. So in this first example, what they're asking you to do is to find the square root of 9. Oh, and when you're done, you're going to make it negative. So they're really asking you for the negative version of the square root of 9. In example 11, this symbol in front, it really means positive and negative. And so they're asking you for both of the square roots of 64. So positive and negative 8. If you wanted to write it like this, 8 and negative 8, you could, but the shorthand would just be like that. So for each of the next examples 12 through 15, come up with what you think the answer would be, whether it's the positive version of the square root, the negative version of the square root, or both. Pause the video, press play when you're ready to check your answers. And so on this next few examples, this is asking us for the positive square root of 25, which is 5. This is asking us for both square roots of 100, so positive and negative 10. This is asking us for the negative square root of 81, which is negative 9. And this is asking us for the square root of 144, which would be 12. In this next example, what we're being asked for is we're being asked to solve for all the possible values of x. So that way, if you square it, it would equal 36. And so if you think of this as like an inverse operation problem, what we could do is we could square root and square root, because whatever we do to one side, we have to do the other. The square root of x squared is x, and the square root of 36 is 6. And we could prove that that's right by squaring 6. So 6 times 6 does in fact give us 36. But there's another number that x could be, that if we were to square it would also give us 36, and that's negative 6. And we could prove that by multiplying it by itself. So the important thing is that when you're looking at a problem like this, you are being asked to find all of the possible values of x. You don't want to let that go. So you're being asked for both the positive and the negative answer. So on the next three examples, examples 16, 17, and 18, solve all of those for x. Be sure to give all of the possible numbers that x could be. Press play when you're ready to check your answer. Okay, so on these examples, all of the possible numbers for x that if you were to square it would give you 1 are both positive 1 and negative 1. All of the possible numbers for x that if you square it give you 49 are positive 7 and negative 7. And all the possible answers for x that if you square it would give you 64 are positive 8 and negative 8. So to prove something is a square root, for example, like the square root of 9, we can multiply the answer that we think it is by itself. And if that gives us that number, we know we're right. So if I'm thinking about the square root of 81, I want you to take a second and write down what you think your answer is. And now take whatever answer you've come up with and multiply that number by its exact self. If the number you think that it is, multiplied by its exact self, is 810,000, then you would be correct. But if not, we have to do some investigating. So I have this feeling that the square root of 81,000 might have a 9 in it, because the square root of 81 is 9. And I'm going to guess that it's 90. And I'm going to check if it's 90 by doing 90 times 90. And I know that 9 times 9 is 81, and that's 2 zeros. So that's actually going to be 8100. So I didn't have enough zeros in my answer. So I'm going to adjust it, and this time I'm going to try 900. And I can check if my answer is 900 by multiplying it by itself. 900 times 900, 9 times 9 would be 81, and it would have 4 zeros in the answer, because 2 zeros and 2 zeros, which is 810,000. So the square root of 810,000 is 900. So if I wanted to find the square root of 400, I would guess that it would have a 2 in it, because the square root of 4 is 2, and I might try 20, and then I would check it. 20 times 20 is going to be 400, which would be the right answer. See if you can come up with the square roots of 160,000 and 4,900, and prove your answer by checking you're right by squaring the numbers that you think they are. Pause the video, press play when you're ready to check your answers. So the square root of 160,000 is 400. What if you accidentally thought it was 800? Well, you could check that you were right by doing 800 times 800, and you would realize that 8 times 8 is actually 64. So it would give you the wrong answer. And then the square root of 4,900 is 70, and you can prove you're right by squaring 70. If you were going to create an example similar to the ones above, you would have to make sure that whatever you picked had an even number of zeros in it. So let's say you had 36, and then maybe 6 zeros, and so then our trick could be to find the square root of 36, and then cut our number of zeros in half. Because I would know that 6 times 6 is 36, and if I have, that should have 3 zeros in it. And then if I do 3 zeros times 3 zeros, that's going to give me a total of 6 zeros. So again, on this next example, if I wanted to find the square root of 0.0121, I would guess that there's probably 11 involved in there, because the square root of 121 is 11. And I might just start with that, so 0.11. And I could try to see if that's correct by squaring it. And so I know that 0.11 times 0.11 is 121. And since there's 2 decimal places here and 2 decimal places here, that means there'd be a total of 4 decimal places in my answer, giving me my correct answer of 0.0121. So this time I'm focused on the decimal places. So if I look at my next example, example 22, I'm going to start with a 9. And since I know I need 4 decimal places in my answer, I'm going to go with 2 decimal places there, because then 0.09 times 0.09 would be an 81 with 4 total decimal places. Now try examples 23 and 24. pause the video, but before you do that, check that your answer is right by multiplying it by itself to see if it would get you the right answer. Press play when you're ready to check. So on example 23, I focused on the 64 to get 8, and since I needed a total of 4 decimal places, I knew that I would need 2 decimal places, because if I did 2 decimal places times 2 decimal places, 0.08 times 0.08, that would give me 4 decimal places in my answer. And on example 24, I focused on the 144 to get 12, and to get 6 decimal places, I would need 3 decimal places, because if I did 3 decimal places times 3 decimal places, that would give me a total of 6 decimal places. So the next thing I can do with square roots is I can estimate them, and I can find the 2 closest perfect squares. I'm going to find one above the number and one below the number. So the square root of 40, I don't know what that is, but I know that 49 is a perfect square above it, and that 36 is a perfect square below it. Then I can try to put the numbers in order from least to greatest, which I've already done. And then I'm going to find the square roots of the 2 perfect squares. So the numbers that you actually know the square roots of, go ahead and find those. And so in this case, the square root of 36 is 6, the square root of 49 is 7. So I know that the square root of 40 would, that was a 6, sorry. I know that the square root of 49 would be somewhere between 6 and 7. And then if I had to pick which one it was closer to, I would pick 6 because 40 is only 4 spaces away from 36, where 40 is 9 spaces away from 37. So you could say that this is between 6 and 7, but closer to 6. Let's do one more together. So for example 26, I'm trying to estimate the square root of 110. Above 110, I know the square root of 121, and below 110, I know the square root of 100. The square root of 100 is 10, the square root of 121 is 11. And if I had to pick the closer one, I would pick 10, because 110 and 100 are 10 spaces away, where 110 and 121 are 11 spaces away. Try examples 27, 28, and 29. Pause the video to do your work. Press play when you're ready to check your answer. So the square root of 20 would lie somewhere between 4 and 5, but it would be closer to 4. The square root of 8 would lie between 6 and 7, but closer to 6. And the square root of 8 would be between 2 and 3, but closer to 3. When we evaluate expressions, we're still following PEMDAS. It's important to remember that in PEMDAS, the reason multiplication and division are on the same level, and the reason addition and subtraction are on the same level, meaning we go left to right, is because they're inverses, and the inverses of exponents is square roots. So if you were to find a square root in a PEMDAS problem, you would do it in the same spot you would do exponents. So for this example, example 30, I'd start by replacing x with the number, which is 81. I have 2 operations. I have subtraction and square roots. So the first thing I'm going to do is the square root of 81, which is 9, and then 11 minus 9 is 2. For example 31, it's important to remember that that's going to be implied multiplication. So I've got 6 times the square root of x, but x is 100, and then plus 3. Also just notice that kind of the hat on the square root just covers the 100. It doesn't extend all the way over. If it did, we would actually add those. But so now I'm going to follow my order of operations. So I don't have any parentheses. So now I'm looking for exponents or square roots, and I have the square root of 100, which is 10. Bring everything else down. Now I'm going to multiply, and then finally I add. Give examples 32 and 33 a try. Pause the video. When you're ready to check your answers, press play. For example 32, we would start this by substituting in 64. The square root of 64 is 8. 8 times negative 3 is negative 24, and then we add 36 to get positive 12. Here we replaced x with 36. The square root of 36 is 6. I'm going to multiply, which is 48, and then 54 minus 48 is 6. So this symbol, square root, means to find the number times itself that equals x. This symbol is a little bit different. You'll see that it has a 3 in there, and what that is going to mean is cube root. And all a cube root is, instead of where like the square root means 3 times itself, you can see that you have 2 factors. A cube root just means you're going to have 3 factors. So you're looking for something times itself 3 times. So if I'm looking for the cube root of 27, I'm looking for a number that if I multiply itself 3 times would give me 27, and that number would be 3. 3 times 3 times 3, because that would give me 9 times 3, which is 27. I want you to try it for example 36. See if you can find it. Oh, whoops. 34 and 36. See if you can find the cube roots of 8 and 64. Pause the video, press play when you're ready to check your answers. So the cube root of 8 would be 2, because 2 times 2 times 2 would be 8, and the cube root of 64 would be 4. 4 times 4 times 4 would be 64. Our next definition for a rational number, so we learned the other day that rational meant able to write as a fraction. The prefix IR would be not, so this means that they cannot be written as a fraction. They are not rational. This would include pi and decimals that do not end or repeat. And those are also square roots of non-perfect squares. So like, for example, we know the square root of 4 is 2, but a square root of 5, say, or square root of 14 even, or the square root of 20. It doesn't have to be odd, or square root of 21. Anything I don't know the square root of would also be irrational. So I'm going to use this chart. We'll kind of go through, and we're just going to check off these boxes. So the square root of 24, I don't know the square root of 24. It's not a perfect square, so right away it's going to be irrational. Square root of 100, well, I know that's 10, and then 10 is whole. It's also integer. It's also irrational if you think back to that chart that we did the other day. The negative square root of 81, so that's the square root of 81 is 9, but then I'm going to make it negative. It can't be whole because it's negative, but it is an integer and it's rational. And keep in mind, something can't be both rational and irrational at the same time. It either has to be one or the other. The square root of 25 and then make it negative, that would be negative 5, so it can't be whole because it's negative, but it is integer and rational. Square root of 30, 30 is not a perfect square, so that's going to be irrational. And then 1/2, it's not whole because it's a fraction, it's not an integer because it's a fraction, but it's a fraction, so therefore it's rational. So anything that's a square root of like 30 or 24, if you were to type these into a calculator, they would give you never-ending, never-repeating decimals, and therefore they are irrational. There would be no way to write these guys as a fraction.